I'm this morning's session's chair, so I'm sure. I'm an assistant professor in BIMSA. Okay, so we are very honored to introduce our first esteemed speaker for this session, Professor Björn Engquist. For many years, Professor Engquist has been a leading researcher in the development, analysis, and applications of the numerical method for differential equations. He holds memberships in several national academies of science. So please join us in extending a warm welcome to Professor Engquist as he takes the stage.
Thank you very much, and good morning. It's been a great Congress so far, and I thank the organizer for the opportunity of being part of that. So I'll talk about optimization, global optimization, meaning that we are not only looking for a local mean, but a global mean, and when the function, objective function, is not necessarily convex. That's been a classical topic in optimization, and now of revived interest because of machine learning. It's the learning in machine learning in this case. So this is work with Qui Ren at Columbia University. He was a colleague of mine in UT Austin, and Yunan Yang, growing up in the city of Beijing, actually, and she is now in Cornell. She was a student at Austin. So let's see if I can. It worked a little while ago, but it doesn't do that now. So we use this old-fashioned technique here. So what I will do is introduce essentially two algorithms of stochastic gradient descent. And there will be two different techniques, and there will be also two different types of proofs of the convergence. One sort of more probability-based and one PDE-based in this case. So our challenge is then to find a minimization of a function. And now we are looking all over the space. We will actually do most of it on a torus. So we have a boundary domain. And we are not interested at this time on the boundary condition. So it's an unconstrained optimization that will be the topic. So the difficulty, of course, is that there is a number of local min, and our classical methods of gradient descent or Newton's method for finding a minimum or a maximum or a function. We will always talk about minimum over here. Easily get trapped then in local minima. So one has to avoid that in some way. And as I mentioned at the beginning, this type of landscape, in the case of machine learning, loss landscape, typically has a number of local minima, and it could look pretty challenging for an optimization method. So these are some visualization of, typically it's in high dimension, and this is of course a projection into lower dimension to see what goes on. So we'll like to try to move around in this landscape in order to find the minimum. So classical gradient descent, of course, you take a step size in the negative direction of the gradient and thereby lowering the value of the function. If you don't go too far, or if the function does have a nice gradient, typically you could prove convergence if the gradient is Lipschitz continuous and the step size is bounded as a function of this Lipschitz constant, and then it converges geometrically. So this would be the ideal thing. However, this of course converges to the local minimum, which may not be the global minimum. So we would like to do something differently, and the natural way to do that is to introduce noise. So you add a random term, scale appropriately with a certain variance, and then Rj here would be a random number. So it's coming from a normal distribution, and this way you hopefully would then jump out of a local mean if you would be forced to go in there. So this is what was done before. You added the noise with the goal of getting out of a local minimum in order to do this. You could also think about the case where the objective function is intrinsically stochastic. So you don't add anything, it's built into the function. This is more the way it is in machine learning, where typically the objective function is a sum of different components to measure the difference to the data in supervised machine learning, for example. And then in order to reduce the computational cost, you, instead of evaluating this huge sum, typically hundreds of thousands of terms, by taking subsamples and thereby introducing, and the subsamples are randomly chosen, mini batch, and this is what would happen. So you will get this. We will also see that it is actually possible if you have a variance that is state dependent, that depends on where you are, adaptive in that sense, to get a method that converges without actually introducing the gradient. And all of the times here we will have the random term will be normally distributed and independent with the different samples. So that's sort of the tools we will be looking at in this case. So here you can see the thinking behind stochastic gradient descent as a way of doing global optimization. So the idea is here that you have, let's see here, oh, it's dead, okay. So the idea here, of course, is that you would like to add some noise term. This is the one we had to the gradient descent. And you need this noise term to go to 0 so that you stay here. Otherwise, you would, of course, never stay here. You would always have a random movement at the minimum. So this is needed for convergence. If you bring it down to 0 directly or too fast, what would happen is that you're here, then the noise term is not enough, so it brings you over to the other side in this case. And if it's too slowly, then you would escape over here as if it would be a constant. So it is a balance between those, and that was typically done in the old days by ad hoc techniques. Now, if you look at this, many ways of thinking about this. You could do methods that converge in different ways. Strongly converge in expectation, it can converge in probability, and you could also think about doing the analysis directly on the discrete algorithm or as a continuum limit via stochastic differential equation or the PDE Fokker-Planck equation to study the probability distribution as a function of time in this case. So that was resolved way back, almost 40 years ago, yes? Okay, see there. Even that works, very good, thank you. Let's see here. I need to go back, which was, no. It's hard to see, it doesn't work all the time here. So let me go back up here. No, let's see here, this way. Sorry about this here. So now we're there. So this was a proof then for quite some time. And that was done on the intermediate level, meaning not the discrete function directly, but the stochastic differential equation describing the limit as a step size go to 0. Or you could think about the discrete algorithm as an Euler or Euler-Maruyama scheme for doing this equation. And what these guys proved, Germain and Wang proved, was that you have to bring down the step size in the earlier one, or the temperature in this formulation, very slowly in a logarithmic way to 0 in order to get the balance of staying in the global min enough to get a weak convergence and not getting stuck in a local min away from the global min. So this was a logarithmic one. There's also a comment there that almost sure convergence cannot be done because you always have to explore the full field. You never, in a finite number of steps, cover, of course, densely the whole domain. So there could be a global min sitting far way out. So therefore, we are looking at weaker forms of convergence here, because in order to have a global convergence, there's no way that after a certain number of steps, you would actually be in the neighborhood of the true for the rest of the iterations. So this is what would happen. This was what we had over here. So the idea that we introduce here is to, instead of just having a fixed variance, have the variance depend on the function. So that's the whole key idea in the talk here. So that would then depend on where you are, and the simplest way essentially just to have two steps over here. So there is a threshold value of the function, and above there we have a larger variance, and below we have a smaller variance. This you could keep fixed, or you could think about infinity, a uniform distribution. That's the way the proof will go, and then the smaller value is then inside, or rather inside the domain that contains the optimum. So the philosophy behind this would then be that when here, if you have this would be the threshold value, let's say, you start earlier and then you come down, then you would have in the domain that is outside the green interval, which is a cutoff domain here, the lower level set domain, and then up here it would be a larger variance, and down here a smaller. So it's rather simplistic in that way. The question is, how would you then do the threshold, the bar here, and how would you do the variance inside this particular domain in order to get convergence? So the algorithm would be, as I mentioned before, that you have these threshold value in f bar here that will be lowered during the calculation, and the same thing also the variance inside the domain that contains the optimal, rather in the lower level set domain in this case. In practice, all the calculations, or not all the calculations, but many of them were just using some algebraic decay in those, both in F and sigma. What you need in order to do that in a rigorous way, you need to couple the Fj here to the volume of the lower set domain. So here you're thinking of an optimum here, it would be the level set. It typically may not look so clean, even for a smooth function. It could be messy, many component part, it could be fractal boundary, etc. But that's not so important here, it's just the volume we'll do. So we have the coupling with the volume, you lower the volume then algebraically, and thereby also lowering F algebraically in this way. And then sigma is also defined based on the volume. The volume as a function of the level set may not be known, typically wouldn't be known, so that it will be explored by a Monte Carlo method that takes the volume into account. And the minimum of the function that is also known will just be during the calculation, the minimum overall history in this case. So that's the way it is done. In practice, it seems to be very robust for anything, but that's needed for the proof. And for the convergence theory, we need that it behaves nicely for just convergence of the gradient method near the minimum. So we assume there it is regular, C3, and also have then being strongly convex, meaning in this case that the Hessian has strictly positive eigenvalues for the function over. Otherwise, we just need that the gradient is defined. So it could be C1, example, outside. So they could be messy and have many local minima, but this is for the final convergence. If we are reducing it to a gradient descent in the limit, then it should also be working around that. And that needs only to be in an open set around the minimum. for doing that. So this is what's needed for the full proof. So the convergence here is algebraic, both in probability here. So this is the probability of being outside a set that is shrinking around a ball that is shrinking above the minimum, and the shrinking itself is also algebraic. So alpha is a positive constant. So that is the alpha 1 and alpha 2. So that's what it is. So here, the proof is in two parts. One has to do with sort of the global nature, and the other with the local nature, the convergence part. The first says essentially that during the history of the calculation, you would visit every open set in the domain. We are looking at a torus over here, so we have periodic boundary conditions in this case. So this would be the thing to cover all the domains, and the rest is a convergence part, is that when you are then thinly, which you never know that you will be in. So it is same algorithm all the time. It is not that you sort of realize that you are close to the global minimum, and thereby you could use some other technique in this case. It just says that when as j becomes large and the limit, then the probability of being outside omega j complement here of the ball around the minimum, or the open set around the minimum defined by this level set formula, goes to 0 compared to going in. So the chance of jumping out is much smaller in the limit than the chance of jumping in from outside, and thereby you get the probability, convergence in probability for this thing. So this repeats essentially what I said over here, that the property 1 says that it will be in the limit dense, and the property 2 here says that you would get this algebraic convergence in probability and in space. And again, this is important. I mean, there are a number of algorithms where you switch from sort of exploring the landscape and then switch to a faster one, and that is a reasonable assumption. But here we are just looking for the raw method, in the sense that you use one algorithm that is agnostic to where you are in the history, whether you are close to the local mean or not. So that's the structure of the proof is rather straightforward in a way. So we think about, we have this f bar. So outside of this domain, the function is larger than f bar. Inside this domain, it is smaller than f bar, and f bar is shrinking, so that this domain is shrinking with the function of j. And now we are looking at the property 1, so we would like to see any positive set with positive mass. We would like to see that we will reach this here with a probability that is away from 0 for a particular j in this case. So if we are out here, then we assume that the random number is uniform over the whole set. Again, think about this as a finite set. It just depends on the ratio between these. So it's a finite. So if you just have j large enough, then of course you would reach that with increasing probability after all these steps over there. The difficulty is over here, because there this is the variance goes to 0 in this area. So the chance of getting out is not obviously large enough, particularly not large enough to reach outside, but the set is also shrinking. So the probability of getting out of the small set, omega j, is then measurable in terms of these algebraic decay. And then in order to analyze it, you cannot do it as a Markov process. You have to include 2 steps so to get enough probability in order to come to the other set. So this would be the thing you are looking at. And the proof is just, I just take one of the lemmas over here. It is just based on conditional probability. But you have to be somewhat careful about this. So it becomes rather lengthy to make it formal, correct. But so the problem is really that here the density function in this area depends on the whole history in this case. And that messes up, of course, the conditional probability argument. But the saving grace is as soon as you come out over here, you cut off the history, because then you have a uniform distribution for the next step. So in this case, it is possible to sort of ignore the small probability of staying inside and going to this guy over here. It is enough to consider the one where the history is gone. And that's the way it is portrayed. So now we come to the other one, and we would like to show that leaving this domain here, where the minimum is, which is defined then by the function being lower than a threshold value, f bar, that the probability of getting out here is much smaller than the probability of getting into that set from the uniformly distributed random numbers in this case. And again, one can rely upon the worst case scenario, and the worst case scenario is when you have a ball and you are in the middle of the board, because then it is much, it's a lower chance than if the set is not a ball and being some fractal thing, because you will then have a closer part to the boundary to get out in this case. So you have to prove that also in this case. Here is the part where the gradient comes in. If you're sitting at the boundary here and you have a random, normally distributed number, it is roughly 50-50 chance to go out or go in. And of course, that's not at all what you can live with, because you would like this probability to go out, go to zero relative to the other one. But then you rely upon the gradient. So the gradient push you a bit in, distance is large enough so that you then, if you're inside the subdomain here, the probability to get out is small enough relative to the other one. So this is where the gradient plays an important role. So this is, again, repeating what was done here. And then the heuristics of, instead of knowing sort of the optimal value that is there, you use the lowest value in order to in the history. And that makes it a bit slower, a little bit slower alpha, but still provable in this case. So a numerical test, you can have something that is not as violent with just a few local minima, and you can have it in other dimension. And typically the test function that people use is some sort of convex function and superimpose then oscillations of more or less violent type. And that is what has been used in the history. So here we have a case now with the coefficient is C is smaller in this case, and then you would have a more challenging problem with deeper local minimum away from this. And this would be an image in the case where, try to look at from the other side. So we have the global min sitting over here. You have saddle points around and local minima away from this point. So if you look at the convergence history, so this would be the probability of being outside. It goes down outside a ball around the minimum. You get convergence, so this was the nicer function, still having a lot of local minima, and this would be the more challenging function. And this would be up here, which you don't see convergence at all, if you would use a Langevin dynamic, meaning a constant variance, and using the logarithmic convergence. So this here gives convergence, but way off in the case where you have a constant sigma. But using then a variable sigma adapted to the state variables, then you can reduce that and do that. So that was the overall game here. And you can see typically how it looks like. in principle, it will never converge perfectly, in the sense that it will almost surely, after some time, it will be close to the convergence. That's the way you prove for Newton's method or whatever it is. This will never happen because you have to explore the whole landscape at its cost. So here you could see the value of the function. It goes down, and here the convergence will be sort of this going down. And then sometimes the randomness takes you out of this and maybe at the saddle point away from that. So you have moving around outside and then sticking to one of the local minima and then moving around in sort of the uniform distribution and then coming to another local minima. So these will be longer and lower, and that's where the convergence is. So if you look at one particular variable over here, then you could see also that jumps around and sticks at the local minima here, and then at the end here, it will be at the global minima. There will be these guys coming up at some time, but rarer and fewer apart. So here you see how the sigma is reduced. This here is a large number. It's not infinite, but the analysis we did it infinite. And then you see how this is reduced inside this little domain in this case. And here, the corresponding function values coming to the minimum. If you go up in domain, it becomes slower. Partly, not so much of because we use the same form function over here. It's not depending so much on the dimension intrinsically, but it depends on the fact that if you take the function here and make a product of it, the number of local minima near the global minima grows exponentially. So it is a much more challenging, even if you do a 1D problem with many local minima nearby, and thereby you would see the scale of this action is much larger number of iterations needed. And again, of course, if you do logarithmic, it would take a very long time to converge. It should be said also here that if you would like just to use uniformly distributed random number, typically that is done in this genetic type algorithm. You take a lot of sample, you do the best you have, and then you run a method that converges very fast, like a Newton method or a gradient descent or quasi-Newton method, all these Broyden variants in this case. But then the area of attraction over here in high dimension, this thing here, that when you start with a locally converging method, will come down over here, is extremely small. So you would need a way larger number of samples of function evaluation than what an algorithm that is adaptive, that actually changes the landscape by changing the variance. So the classical way of just sampling in order to find where the local global minima is and then having a method would be orders of magnitude slower than having this kind of approach in doing this. So now that was the first part, and the idea was that we had gradient descent, we added a random component for have the global minimum, and by choosing a particular way of adaptive variance depending on the state, we were able to prove converging for the discrete algorithms. So now we saw that this was a powerful way of going from logarithmic to algebraic convergence. So the question is, can we focus on that part of the algorithm much more than we did in the earlier one? And the idea here is now to skip the gradient and just have the noise term in this. Important then, of course, is that we have an adaptive variance. Otherwise, it would just be Brownian motion, and we will not get any convergence. The x will just move around randomly and cover in a uniform way in the limit the domain, and we have no convergence at all. But we saw in the earlier argument that this was pretty reasonable. So let's look at that. We only needed the stochastic gradient descent, so the gradient part of stochastic gradient in the case there. So finding, covering the domain should be fine, but the convergence part, of course, where this or there, one need to do something differently. So now we have an algorithm that doesn't push you inside, but it is uniformly distributed, so it can go in any direction in this way. So it sounds sort of counterintuitive that can actually get convergence because you would like to get to the global mean here, but this is uniformly in terms of radius here or angle distributed random numbers. It takes you everywhere. And the only way that this would happen is the history. So you cannot do a convergence proof on the discrete algorithm step by step by sort of a Markovian type argument. So it is the history here. So what would happen, of course, is that this xn, when it moves out here, it will then have a larger variance and thereby easier get in this direction or vanish away. And if you're in here, it will have a smaller variance. So it is that history that then gives you a probability distribution in the end that you can then get to converge in this case. And this means that we have to leave the discrete version and instead look at the stochastic differential equation as a limit of the discrete variable. Then the step size go to 0 and analyze that instead. And what this would be, we base it then on eta calculus, which would be the reasonable choice here rather than Satonovich for this type of discrete algorithm of that sort. And then we will not work on this side, but we will only look at the density of this stochastic variable, and that is given then by the corresponding Fokker-Bank equation, which will be a parabolic equation here, and by where d here is then related to the sigma that we chose to be algebraic plus a term to avoid 0. This would mean if we have 0 over here, then the d as for stationary would not have finite mass. So this will have a positive setting. So this is what we're going to analyze. So we take a look at this problem over here, and we'd like to see whether this converges in some sense to Dirac at the global minimum. So we take this pseudo-stationary solution for a fixed t here in epsilon t and look at that. That would then be when this is constant, because we have periodic boundary condition and the mass of u. So u would be normalized, and otherwise it would be the inverse of the d term, which is then related to the sigma in this case. And then we are interested, so this here, of course, since as epsilon go to 0, this will then converge to a Dirac around the global minimum. F is now normalized so that it is 0 at the global minimum and positive for all other values. And in order to avoid the singularity, when these may not be this may not be finite, we add epsilon. It also regularizes the algorithm. So now we would like to see the convergence to this stationary value. Then we are happy, because as we lower down epsilon, we will then converge to a Dirac. So we just look at, substitute this term into the equation, multiply with dv and integrate by parts. So we get this integral estimate of the change of v with respect to time expressed in other terms that we know. So this is what we would like to do. So this is a weighted norm, a weighted L2 norm, the one that we will work with, and that's the time change. And then we have the other terms. This came from the chain rule, where we take the derivative not on the v part, but on the d part. And this comes then from the stationary piece over here. And this is the right-hand side in the parabolic equation. So these are the good terms. So this we'll keep. This is what we will estimate. Let's call it E of t for later reference over here. This has a good sign because we will lower the epsilon here, meaning that we're sharpening the variance to focus more, so that the stationary PDF would focus on the direct. So this is this term. And then we can throw away because it's the right term. So we have to estimate the term here, and then here we have a gradient. So we like to do some sort of Poincare inequality in order to do that. And for Poincare inequality, we use the fact that we had taken out the stationary value so that the integral of E is 0 and d is positive but small. And then this here is the explicit form of the pseudo-stationary function. So the Poincare inequality, we are interested actually in to get the constant right over here. So we use a form of the Poincare inequality of Peris-Herrera. I don't know how to pronounce it. That's pretty recent. That is expressed in terms of this particular sort of AP estimate that's called expression. And that enables us to get the constant term here that depends on epsilon, and that's what you get the algebraic decay in the end. So this is the way. And then there's general calculus type thing argument in doing that. So I'll come back to that. And this is rather explicit. We use the fact that, again, the integral of v is equal to 0. So the mean over the torus is equal to 0. And then we just grind on with calculus argument in order to get an estimate of that. If we do that all the way, then this was the thing we were asked. So the estimate will be in a weighted norm for E, and that's it over here. And we have this term sitting in there. And then we have the dependence on the epsilon t term over here, and it sits there. This is the derivative over there. So we get an ODE that we would like to estimate. So use the explicit form of the ODE and stick in the term, use the explicit form of the constant in the Poincare inequality, and then you can write it out to see that you get this algebraic dependence on gamma. There exists then a positive gamma that lives in a certain range. So if you choose epsilon, which was a design parameter in the right way, small enough essentially, then you would get a gamma with the decay. So that means that we will get the decay to the stationary value that is algebraic in this case. And then you use the outside estimate to get the estimate of the same type as before, but instead in the continuum as t goes to 0 in this type of argument. So if we now see the calculation as it is here, you could see that this is a landscape. It's a challenging one with a lot of local minima. You could see that if alpha is small enough here, then we easily satisfy all the conditions, and you will get a convergence. If you increase alpha, it's harder to satisfy the strict conditions in a function, but you converge faster. And if you go too large, this almost goes up, and if you go to the next one, then it will not converge in this case. So it follows the outline of the continuum at the end. So this is, of course, run with the discrete version in the case, or you can think about it as a numerical Euler scheme for the stochastic differential equation. And this is the formula over there. And this is a convergence rate, again, for different alpha. This is a 2D objective function. Interestingly, it converges if you take epsilon to 0 directly. Then the argument doesn't work. The mass of the D inverse is infinite. And there is no known Poincaré type inequality in this case here, but it converges in practice. So it's an interesting case, and I'm not an expert on Poincaré inequality, but checking with Luis Caffarelli, who worked on it a lot, and Alessio Figalli, they have no clue to do that. If not, the minimum would be a cusp of a sharp nature, but anything that is in here strongly convex, meaning positive Hessian, there is no way of estimating this according to that. There are some very special cases for very special functions where it's possible to do, but it is not of any general nature. So that's open. Well, why does this do better than the other guys as a theoretical issue? I have to give up there. Worked quite a lot on it. So, and again, you have this convergence history. So this is a history of the min of f over history. It goes down, and here it stays during the calculation where it jumps around at a local min, another local min, and then at the global min. And you can see also that it stays near these local or global min and does exploration where the randomness kicks it out. You can also see from this type that typically if you have a function where you know that the minimum is 0, very much so it's in over-parameterized machine learning, then you know that you could fit it. So you have a 0 of the loss function. And if you don't know, if you know it for other reason, then you get a faster convergence because you don't have the perfect estimate of the minimum. So here it is estimated by taking the minimum over the history. In the limit, of course, this estimate becomes better and better, and therefore, after some time, some number of steps, then they are the same in the convergence. But in the beginning, knowing the global minimum, which of course you don't know, because if it's not a special function, you know that you actually have enough parameters to fit the min, like in machine learning, then it is a bit slower in doing this thing. So now you could go back and say, well, this had another benefit, and that is that you don't have gradients. If you don't have gradient, and so, I mean, if we again go to the machine learning, then you have all the tricks of getting, by automatic differentiation, getting the gradient out. But in general, of course, that may not be known. So having a method that convergence gradient free has a benefit in itself, where there is no gradient term, but just have the variance sitting over there. So the question is it good to have some gradient information? Of course it is. So if you know the gradient, it would do a faster job, as we did in algorithm 1. But even here, it's better. So if you take the most simplistic version, you take a gradient just by doing one divided difference. Typically, you would need the number of divided differences in the order of the dimension of the independent variables that you're working with. But if you do the simplistic one, you could see that you converges much faster than if you are using the fully gradient free. So this is not to promote this particular algorithm. So it was more to prove that it's actually possible to get convergence both in probability and in space for an algorithm that doesn't know the direction of the gradient in this way. But otherwise, adding some information of that improves if you're thinking of a practical result. You could also compare with the earlier one. So if you go back to the earlier algorithm, where you had a step size in function, we have two values of the variance, one above and below a certain threshold value. And here we have a continuum. So we had f to the objective function to a constant alpha depending on the dimension. But if you then have this type of variance that we had in the second version, the gradient-free version, and use that in the earlier one, it actually does better than the discrete one. However, there is no way of proving convergence then on the discrete algorithm directly. So you have to go just look at the limiting equation and see what it is. It's like when you do a finite element to finite difference method, instead of looking at convergence of the numerical algorithm, you look at stability, etc., coercivity of the PD itself, and only that. So to mention in the beginning, oops, mention in the beginning that, or somewhere in the middle, that one typical way is that you have a uniform distribution, and then you take the starting at the point that has sort of the lowest objective function value, you launch another algorithm, and that is sort of a genetic algorithm, and other versions where you have that you launch an algorithm that is faster to converge. So if you have a lot of samples over here, there should be one close to the local global minimum in the contraction of the global mean, and then you have a faster algorithm doing that. So you could then think about the techniques here, not only as a way of getting in the limit the minimum, but getting faster into a domain where you can switch to a faster method. And usually it's in the business called these two phases, exploration and then exploitation, the latter one where you are in an area where you can have a faster converging algorithm that does that. So you could actually use the earlier algorithm not only as a converging in itself, but in order to improve the time to convergence and the convergence rate at the end. You could use it to launch it as a beginning, as a exploration type algorithm. Here we get it. So with one of the typical functions where you look for minimum, it's a challenging one. There's a lot of local minimum close to the global minimum. Of course, in the true cases of, let's say, machine learning, it doesn't look like that smooth, but there still could be a lot of local minimum near the global minimum in this case. There it's a different story coming in here. And now we can see the two methods working here. There's more of a uniform style exploration in the beginning to find the minimum, the domain actually of contraction to the global min, and another one which is then in the more like the algorithm we wanted to do. So this was a random choice, and then this would be this MCMC one, Markov chain Monte Carlo algorithm that mentioned is in the second phase. If you then add gradient descent to the lowest one that you had, which will be sort of exploitation in the name of this business, then you say, of course, do a much better work over there. So it is a better way of guiding you into the domain where you will set convergence. So one could again see what does it mean for machine learning. Stochastic gradient descent was introduced in the beginning in order to reduce the cost, as I mentioned, because the cost of evaluating the objective function, if we look at supervised learning, the function could have hundreds of thousands of terms which you need to evaluate, and they could be then quite complex because you need to run through the whole network in itself could be in the hundreds of thousands or millions of flops. So therefore, in order to reduce that, people use this mini batch that they took samples out of that as a way of reducing the computational cost. Then it turned out that when you then had more computing power and didn't need so many data points, so you could the larger batches, meaning that you did a better job with the gradient. Things got worse in the way of generalization error. So that you were in a case, you may find a better minimum, but that minimum, from the point of view of classical optimization, was not as good as maybe a local minimum that is more flat, in a sense. That became the heuristics, and there is some supporting analysis that says that you would like to do that. And this type of algorithm where you have a larger variance away from the minimum area, if you look at the Fokker-Planck equation, it will then give you a probability density that is focused on areas where the gradient is, with respect to the parameters, is smaller. And if the gradient with respect to a parameter is smaller, then there is a relation then to the gradient with respect to x. And that is, of course, what the generalization error is all about. You would like to have, if x moves a little bit outside, meaning if you're not in the training set, then you would like to have a value that doesn't change so much. It actually does that. So that is what we are looking right now, but there's no final result in this. So if we finish this up and conclude here, so we looked at the method where the whole idea here was to deal with global and not local convergence for optimization to find a minimum. And we did that by having a variance in the stochastic gradient descent algorithm, or the stochastic descent algorithm without gradient, being of the nature that you had a lower variance, of course, for lower values of the objective function. And that was done in an algebraic setting, so that also the convergence in probability and in space became algebraic. So the idea was two settings, one where you could do it for the discrete algorithm, and one where we could do it only through the limit and on the Fokker-Planck's level. And then a number of examples to do this here. So that's where we are. Thank you very much for this.
So is there any questions?
Hello, Professor. I have a question about your gradient-free optimizations. So you say that you just order some random chaos term in your gradient-free method, right?
So explain a little bit more what you want. So yeah.
So my question is does the work for, because it's independent of the gradient, right?
Yes.
Does it work for the very rough function? For example, the Weierstrass function, very rough. Does it work?
Well, it works for very rough function in practice. So what we need is the ability to go from the discrete algorithm to a stochastic differential equation, and from there to the Fokker-Planck equation. So that imposes, if you want to do the analysis, imposes some constraints on the regularity in this case. But otherwise, it is essentially independent from that, and it sort of just works on the, but it's the aggravated time history that comes in, which is very clear in the Fokker-Planck setting. You have linear parabolic equation that depends on the parameter, and the parameter is the temperature, so to speak, in that setting where you enter, and make it more and more concentrated and direct. So yeah, the regularity doesn't enter into the estimate, more that it's possible to do this transition from discrete to continuum for theory. Yeah.
Okay, thank you.
Hi, Björn. So in one of the experiments you show when you have many local minimums,
Yeah.
the convergence becomes slow.
Yeah.
Does that in the theory in your proof you don't see this, right? You don't see how many local minimum.
No. You don't see the many local minima there. You see it in two ways. So one is the dimension. Alpha and beta, if you look there was a D sitting there in some way. And the larger the D, then the slower convergence that you get. So the dimension comes in there, and that's particularly to do with the volume of the sub-level set domain compared to the full domain.
But in your experiment is 1D, you already see.
Yes, yeah, no, so that has that is one term. The other term is where that is seen even in 1D, and that is that we assumed strongly convex, which means that in the second derivative is bounded away from zero. So you have a sharp form, and that of course blows up when you get more and more oscillatory, more and more centered, and that has to do with how it looks like at the minimum in this case. So it comes in through the back door in the formula, not explicitly the number of minima, no.
Oh, could it be because you have to estimate the volume fraction?
Yes, yeah.
When you do MCMC, when you have many local minimum, the estimate of the level set, the volume of the level set below that F bar could be harder and harder.
And it's also less representative for the behavior. So that estimate plays a role in the final convergence. And away from that, it is less representative of the min. So if it is this that way, yeah, it is. So if we are up here, I cannot be too close to a wall here. So, then of course the parts contain other pieces of this interesting acoustic phenomenon here. We should discuss that. And you only sort of get a coupling between how this domain decays with decaying F here in the case where you can, where the Hessian plays a role. So it is, but of course we didn't need it up here, but here it kicks in to describe it. So therefore it sort of emulates that it should look, because it's quite large here compared to this, that it actually, for the analysis, looks like a minimum like that. So yeah, it comes in that way.
Is there any other question? Okay, if there's no other question, let us thank our speaker again. Okay, thank you. We will have a 15 minutes break, and the next talk starts at 9:45.